Hello everyone, welcome to this video where we are going to talk about virtual machines, emulators and all this stuff, and we will try to make our own virtual machine, a very old one called CHIP-8, and we will see how we can do that and we will learn these concepts. So Orko is here. Orko, let me explain the format to you guys. See, Orko is here as the proxy of the audience, right? So it's beneficial for me that I'll explain it directly to Orko and he can ask the questions that may come into anyone's mind. And Orko has truly not seen the code before and he has very less idea of what we are exactly going to talk about today. Orko still has no idea why he is here. So
he spoke my mind. He just dragged me in here. So
yeah. So
I'm just trapped as you are, who is watching this video.
So guys, watch this complete video and it might be a long one, so the timestamps would be there in the description. So feel free to see which timestamp you want to the section you would like to watch. All right, so let's start by talking about virtual machines, and we will go to CHIP-8 and we will write the code for that. But let's start with talking about virtual machines. So I picked up this, the definition from Wikipedia. And it says that like it's a emulation of a computer system, and it emulates a computer architecture, physical computer architecture through software, right? Now, the thing about virtual machines is that it might be emulating some piece of hardware, like you use VMware or something like that, or it might be a platform, kind of a theoretical machine that has been defined and then it has been implemented in software, like JVM. Java Virtual Machine is also a virtual machine which helps us run Java code for every kind of platform, because it's a virtual machine and it sits atop the OS, right? So
yeah, okay.
In one line we define the hardware architecture in code. So before going into all this, some people might not know the meaning of architectures and stuff. If you have done any college course in some kind of computer science or something like that, you will know all this stuff. But so architecture, and also I picked up another definition from Wiki. And
Wikipedia, obviously.
Yeah, come on. You think I would sit and write presentations myself?
Yeah, this presentation will be sponsored by Wikipedia.
So they say it's a set of rules and methods that describe the functionality, organization, implementation of computer systems. Now, architecture is something like, let's say, how much RAM a kind of computer can hold, what kind of instructions that the CPU might the CPU might execute. All these things are defined in architecture. Now we have to also keep in mind that architectures also can be theoretical. It doesn't need to be put in circuits and an electronic machine. It can also be theoretical. So some basic components of an architecture, and you obviously know all these things, right? Like CPU, registers and RAMs. So when defining an architecture, we define all these things, like what set of instructions should the CPU for that architecture solve, or how many registers we have and why I use these registers. Now registers are very small memory units that are very close to the processor, and they are extremely fast, and they are used for special operations by the processor. And RAM, as we all know, is a big memory unit that stores the running program in that, and it's volatile. When we turn it off, it goes away. So these are some components. There can be buses, there can be video memory, there can be other components that make up a complex architecture. But these are some components, common components that every architecture has. So every architecture, the way we differentiate in architectures, like x86 is different from let's say AMD 64, in way that the instruction set may be different. Like the instructions that Intel executes versus the instruction set that ARM executes, right? These two might be different, and that's what makes them different, and that's why we need different binaries for both of these systems. So as I have told here, that every program, whatever you write it in, let's say you write in something in Java or you write something in C++, at the end of the day, it has to be compiled down to binary code. We all know that, right? And what do this binary code, what is this executable file this contains? It contains instructions, or in the language of processors, opcodes. These are instructions and opcodes directly for the processor. Processor sees these instructions and then executes them. And that gives rise to all the complex systems and all the complex software that we have. And an emulator or a virtual machine takes a specific architecture and implements through it through software. So let's say there is an architecture which says that I have got 4 opcodes, 1, 2, 3, 4, and it has 3 registers, and it can have maximum 10 kilobytes of RAM. So we can define something like this, that 3 registers are actually 3 variables. The RAM is an array, which I'm mentioning in software, and then I read all, and I take the executable for that architecture, some executable, some program, and I read each instruction and execute them in software. So as I told you, for our example architecture, there might be only 4 instructions, 1, 2, 3, 4. So we did 1, 2, 3, or 4, and we put some switch case in our software, in our code, and we emulate that. So this is a very simplistic view of emulation. And imagine, so there are this x86 and all these are so complex architectures, and people have still wrote software to emulate them, perfectly, like VMware and all these things. So Orko, any questions till now?
Nope.
You didn't read the script, man. Script had some questions.
Script. Goddamn script.
Come
I'm
on,
too
man.
smart.
Read the
Too
scripts I send you. Read the scripts I send you. Come on. So as I was telling, that a virtual machine can not just emulate some hardware, but also maybe just a theoretical virtual machine that has been defined in software only, right? So the virtual machines which actually emulates a real system is called a system virtual machine, like VMware. But the other kind, like JVM, is actually it's called a process virtual machine. There is no hardware for JVM. It does not emulate a hardware, but it's a virtual machine nonetheless, because there is a theoretical model for a system, for a machine, and it implements it in software. So let's talk about CHIP-8. So CHIP-8 is from the golden times of 1970s.
Yes.
And it was a process virtual machine like JVM, but the architecture of this also gives us a feel of writing a system virtual machine, because the way it's developed, because of the way it's written. And it was made for computers like Cosmac VIP, so that developers can easily write games for those systems, for these 8-bit computers. And actually developers wrote games like Space Invaders, games like Brick for this, and at the end of the video we will play Space Invaders. So
yes, I'm here for that part.
I mean, I told you that I will buy you a Minecraft for this video. You know that, right?
Yes,
just for appearing in this video. Just joking,
yes,
guys.
my appearance has cost.
Yeah. So when I said Minecraft, I meant Space Invaders.
Okay.
On a CHIP-8.
That's a letdown. CHIP-8 is a funny name though.
CHIP-8 is a funny name. So we will implement this in JavaScript, and we will see how can we do that. So let's say we will be building something like this. So this is a game called Blitz, and it's like dropping bombs on buildings. I haven't mastered the game quite yet, but yeah, dropping bombs.
Wrong game, man.
dropping.
You will be cancelled.
Yeah, I mean, these are evil buildings of evil people, and that's,
Okay, yeah, let's just assumptions.
yeah,
Yes.
evil buildings, and Space Invaders also there, which, you know.
Nobody's trading in these buildings.
Right. So, first of all, shout out to this article from which I mostly wrote all the code. I link it in the description and you can go read it. So, let's get actually started with building our CHIP-8 virtual machine with JavaScript. So, well, we are here with our code editor, VS Code, and I've installed some extension which shows some browser in it. So, first step of virtualizing any architecture is to get all the specifications of that architecture, right? So this is kind of the specification that everyone refers to of CHIP-8 that I found on internet. And it tells us that like what kind of, like how much memory it has, what's stored in the memory, what kind of keyboard it uses, what kind of display it supports. These are something called sprites, by the way.
This website, this website has not been updated since 1970s.
No, this
Look,
is
it's got HTML format. What the?
okay. This website is seriously from 1997 when we were born.
Oh yeah.
So this website is as old as we are. There are
Oh.
some, and all these instructions, all these opcodes that we will be writing down in our software. So I will not probably write the full code. Some pieces of code I'll write, some pieces of code I'll copy from the code I've already written. I'll link the GitHub in the description, which you can go and see all the code. So let's get started with it. Now, just to start, these are the folder structure that we have. So I have put all the ROMs in here, and ROMs are basically the programs, the binary files for CHIP-8, right? And the source has the files that we will be implementing one by one. I have pre-filled the CSS here because we don't need to go through the detail of that, do we? And our index.html file will be the starting point. So here's how we will do it. We will first implement the monitor, the display, and then we will go forward with the CPU. Then we will go ahead with the keyboard, and at the last, the speaker. So first of all, we need a screen on the, on our web page. For that, I will use something like, so what I've done here is I have, for this, in this div, I have written this title with the emojis that we saw in the original page that I showed you. And then I have used a canvas. So in this canvas, we will draw out whatever we need to draw, and we will use this as a screen. And I've also linked the index.js script that we will be implementing. So before index.js, let's actually implement our monitor, right? So I'll define a class here, class monitor. Let's export the class.
Class monitor word gives me nightmares.
Yeah, man. I didn't realize this while writing this. So in the original code, they use the class name called renderer in that article that I showed. This is why.
This is why.
Okay.
It's just NAM flashbacks.
Damn, man, I didn't realize this. So in the package.json, what I have done is I have installed parcel to bind all the modules, and there are 3 scripts: start, build, and build and serve. The start script just starts the parcel dev server. The build script, builds all the files and puts it into the dist folder. And build and serve actually builds the file and starts a small node server to serve that. And there are some reasons why I'm using a node server rather than always using the parcel dev server. This static files per part you see is for this parcel plugin for statics files. So what it does is it will copy this ROM folder inside our dist folder, which we can then deploy, right? So let's implement our monitor class. Okay. So let me write the constructor. And what we will be taking in this constructor is the canvas, right? This canvas would be our usage, that we will use this canvas to, you know, write to display everything that we show. So the monitor would actually contain all the data. The class will contain all the data that we want to display, and then we will display all the data on the canvas at the end. Okay, I cannot actually find a good position for this mic and type on my keyboard. So let's just define some things in the, like, this dot calls is calls, and this dot rows. I don't know, I have got all the things in constant, and why do I put it in this? I have no idea, but I've written
Why?
But I've written it this way before when I was writing the code, and now I am referring to that code, so I won't change it now. Make sense?
Yeah.
Right.
Sure.
So
Whatever you say. I'm getting my space invaders.
So you see, I have defined calls to be 64 and rows to be 32. And where does it come from? So if we see in the display section of the architecture specification, we can see that there are 64 columns and 32 rows. It starts from 00 to 630 and goes up to 6331. And so we will keep following this specifications and do our thing accordingly. Now let's have a display buffer kind of thing, which will contain the data that we want to display. Now in CHIP-8, let's say there are 64 pixels wide and 32 pixels tall. Each pixel can be either turned off or on. It has no colors or stuff like that, right? So it can only be turned off or on. So I'll just declare it as an array, and I will make a size of this dot calls, this dot rows. It's weird to declare arrays like this in JavaScript, but just for better understanding.
Yeah.
I'll also initialize this scale. Again, I'm using a constant in this, putting a constant in this. I don't know why still. So why we are using scale? Because see, in those days pixels were pretty big, so we could actually see them. Nowadays pixels are very small, so we will have to multiply the pixel value a bit by I've chosen a scale of 15, so each pixel is quite big so that we can actually see them in our modern devices. Now let's go ahead and give the canvas a width and a height. I'll actually not type this code out because normal web dev stuff. So I'll copy paste this code. So what I've done here is I have changed the width of the canvas to the number of columns to multiplied by the scale, and the number of rows multiplied the scale. And I have also taken the canvas context. So canvas context is what we use to draw stuff on the canvas, right? Now let's go ahead and call a function, define a function called setPixel. So in setPixel, what we will do is we will take X and Y and put that pixel on the display. Now in CHIP-8, what they do is, let's say you have the array of pixels or array of things that you want to show. Let's represent them by 1 and 0 because the pixel can either be turned off or on. So when I say set pixel X and Y, it does not hearing it, one might think that it actually takes that pixel and turns it on. But no, what it does is it takes that pixel, what we are mentioning here, X and Y, and it performs an XOR with it with 1. So if so it's just to toggle the pixels and also detecting if two sprites are overlapping so that they might detect collisions. So if 1 and 1 collide, two sprites like that collide, they detect a collision. And I'll show you why that is. So let's say what I'll do is, now you see the display array that we have is this dot calls into this dot rows. So it's actually a flat 1D array. So we will take those two coordinates and we will if you have read computer science, you will also know about this row major formats and column major formats for storing 2D arrays in 1D arrays. So we will use this is simple math, and we will use this column major format where we will encode this 2D pixel value that we have, 2D coordinates we have, into this 1D, and then we will XOR its value with 1. Sorry. I can't type, and I can't type with this mic out here. All right, and so this function also should return something, and that's, is the pixel turned off or on? So if the pixel is turned off, if the pixel is deleted, then we will actually return true, and if the pixel is not deleted, if the pixel is still 1, then we will return false. So we will say this dot display x plus y into this dot calls not equals 1, and we'll return this. Now the CHIP-8 also has the specification that if the column values and the row values are out of bounds, then we should just wrap around them. So we have to put this piece of code where we check that if it's if it's greater than the column, then we just wrap around, right? We will also use a function called clear. So what will this do? It's simply clear out this this full display. So we'll just say this dot display equals new array like with this dot calls into this dot rows. Simple enough. And then we will define a function called paint. Right. So this paint function would actually put all the pixels on our canvas from the this dot display array, right? So let me copy the code here. So what it does is, first I will clear the full canvas and paint it with black. Actually, we want a black background with white pixels on it, and then we will iterate over this this dot display array, and if we see that it's 1 or that pixel is turned on, then we will draw a white rectangle in that place representing a pixel, right? Let's also put this function in called test render, with which we can actually test that if this function is working or not, if this class is working or not. All right, so let's try to put in our make use of this monitor class, and we'll go to our index.js file where we will put the glue code to use the monitor and everything. So let me import the monitor from monitor, and then make a class out of that, object out of that. Now as I told you, our monitor needs the needs the canvas reference, right? So we will just put document dot get element by id screen, and we will now call monitor dot test render just to see if everything works fine. Now I have put this npm start call to actually start a dev server, and we will check it out. So they say cannot set property width of undefined. Now why is that? Let's try to find that out. So as the browser said, the problem is that it said that this dot canvas is undefined, and that's because we haven't actually done this so that it works. And hey, look, now that this weird thing is working, and we can see that actually our test render is working now. Right, so let's close this out and we can continue. So now that we have done and we are done and dusted with the monitor, let's go on to the interesting part, to the CPU. let's go to our CHIP-8 class, CHIP-8 file, and we will actually define this CHIP-8 class. Export default CHIP-8. So now we will go ahead to this to the specification, and we will encode all the instructions. But before that, we have to encode the data structure. So what do you mean by the data structure? This data structure, or the structure of this CHIP-8 class, would represent the actual hardware. So what has been said in here? It says, I cannot find the exact place. So it says that it has 4096 or kind of 4 kilobytes of memory, and it has got 16 registers, a 16 level stack, and we will actually implement those in our code. So let's go ahead and do that.
My makeshift light just stopped working. It's out of battery. This is what happens when you don't spend money on lights.
You are just sitting there anyway. You're doing nothing, so doesn't matter.
Oh my god, it hurts my feelings. Okay.
It was meant to. So let's start with the memory, right? So the memory is actually the RAM that the CHIP-8 should had. Not RAM, kind of, let's just say it memory, because CHIP-8 is a theoretical machine, so everything that it has is kind of its RAM. So it will be a 4 kilobyte memory, and I'll define it as a uint8 array. So a uint8 array is actually a kind of a typed array in JavaScript, and each element of that array is 1 byte long, as the name says. So this actually helps us to get 4096 bytes of memory, which is specified in the specifications for CHIP-8. Now let's have the registers. Now all the registers in CHIP-8 is actually 1 byte, 8-bit registers, right? So we will go ahead and we will make an array, uint8 array for the registers. So we are done with the memory, and then we are done with the registers. Let's go to the next thing. There is a 16-bit index register, and we will see how we will use this index register later when we are coding the instructions. And then there is a very interesting thing, guys. This is called the PC. This is a 16-bit program counter. So this PC, or the program counter register, is like a pointer to the line of code that is being currently executed, right? So wherever this PC points to, that line of code would be executed. Now if we go ahead and take a look at the memory map of this this CHIP-8 documentation, we will see that 0x200, we write 0x to mention that what we are saying is actually in hexadecimal or base 16, not base 10, which is the decimal number system. So as it says that any program that is loaded into the CHIP-8 memory, any ROM that we load on, should start at 0x200. So we will initialize our PC at 0x200. And now why is that? That's just the specification that we should point it. So the first position where the code will be would be 0x200. Next up, it has got a 16 level stack. Now we will just define this as a empty array in JavaScript, because we can use this actually as a stack. Now generally in C, C++, or if you're using Java or something like that, we will have a array of size 16, and then you will use it as a stack. To use that stack, there is also this register called SP, which is also a 8-bit register. This is 8-bit register,
pointer,
which is the stack pointer, and we will actually not be using this. I've just written this just for clarity and understanding, because we will be using JavaScript, stack, push, pop, and all those things.
Yeah.
Right. There are some timers called delay timer. Now, I'm not sure why the delay timer is there, but I guess because of the animations and smooth animations, that will be there in the games. Right. And there is also another timer called the sound timer. So the sound timer is actually there to play sounds as it shows. So if the sound timer is set to 5, then that's a particular sound, and in CHIP-8 there are very basic support for sound. So the sound would play for 5 cycles, five CPU cycles, and we will come what these CPU cycles exactly is. Then we will have to also declare our keyboard. We will later come to that, and also we have to declare inside this our monitor, because we will be using our monitor. So let's just take in the monitor through the constructor and initialize monitor to be that this monitor. So it just tells us this is just gives us handle to use the monitor, and there will be a lot of instructions that will use monitors to either clear that, put some pixel, or load some sprites, something like that. So we will have some more variables called paused. If the system is paused, this is also actually a part of the CHIP-8 architecture. And we'll mention something called speed. This is what we will use to control the speed of our CPU cycles, and I'll get to CPU cycles later in the video. Now we will actually implement our instructions, right? This is the most interesting part according to me. So let's go to the instructions part, right? So they have first defined some values, some terminologies. So they say that ADDR is a 12-bit address value. N or nibble is a 4-bit value, and then we have got X and Y. These are also 4-bit values. So these letters and these terminologies are used to represent these, instructions or these opcodes, right? So what you see here, 0NNN or 00E0 or 00EE, these are actually the hexadecimal value of the the hexadecimal value of the instruction. So the ROM would just contain these numbers represented binary. All things are represented in binary in computers. So it will just contain these numbers. So let's say it's a program, so each line of the program is actually a number, and each hexadecimal number actually represents a instruction. So as we see that 1NNN is an instruction. What does this mean actually? So first of all, each instruction is actually 2 bytes long or 16 bits long. So 1NNN means that there is 1, and each hexadecimal unit or each hexadecimal digit that we are considering that it takes 4 bits. So this takes 4 bits, and this NNN means a 12-bit address that was said here, right? NNN or ADDR. NNN means a 12-bit address. So there will be 1 at first, and then there will be a 12-bit address. So when we are executing, whenever we see that the first hexadecimal, the first part of the first 4 bits of the instruction represent 1, then we will take the next 12 bits from the 16-bit value, and we will execute this JP ADDR instruction, which means the PC is set to that address, or it jumps there. So like in C we used to have goto or something like that, right? And we will put a switch case here first of all and try to understand that. Now you might maybe want to skip this part, some people, because I like to talk a bit about binary values. Maybe for some people it won't be clear, the binary operations that we'll be doing. So let me take a section to just clarify that. So let's say I have a instruction something like FF AA. right? Now let's say this F means opcode, this, and we need to extract this FAA. Now how will we extract this part? We will be using the AND operation, right? So how will we AND it with? We will AND it with 0 F F F. Now why did I AND it with this? F in hexadecimal, when translated to binary, becomes 1 1 1 1. Am I right, Orko?
Yep.
Yeah. So when we're doing this operation, what we mean is F. So what will be the answer of A and F? It would always be F, because F is 1 1 1 1 and A is also something like that. I think it's 1 0 1 0 A. So 1 0 1 0, and when we AND it with 1 1 1 1, we will again get 1 0 1 0, that is A. So any hexadecimal digit, let's call it digits, any hexadecimal digit ANDed with F results that digit itself. So what the result we will get here? We will get A here, we'll get A here, we'll get F here, and we will get 0 here. So
I think the second part you are ending it with is called mask, right?
yeah, we can call it a mask, right? Yeah, we can call it a mask. So you see that with ANDing it with 0 FFF, we actually got 0 FAA. So FAA is the value that we wanted to extract. So again, let's say a scenario that we have is F 1 8 A, and we want to extract this 1 and 8 value. And there is a very good reason for that. There are some instructions in CHIP-8 which has this X and Y value. This X and Y values generally represent a coordinate, maybe which register to use, something like that. So let's see this, like 8XY0. So X and Y are 4-bit values that we'll have to extract. So this might be some case like this, that this is F, maybe X is 1 and Y is 8, and we need to extract this X and Y value. And how we will do it? Now Orko, you tell me, when we, like last time, what should I AND it to so that I get 1 and 8? So let's say let's target for X now. So what should I AND it with to get that X value for now? Just to zero out everything else. So what should I AND
the X value?
X value or 1?
Yeah, ended with F.
So we want only X and the full mask.
Yeah, it's 0F00.
Right, so we'll get 0F00. Now what we get at the end is 0 1 0 0, right? Now you see, we want only 1, so we want only 1, right? We don't want 1 0 0. So how we will do that? So keep in mind, guys, keep in mind, this F, this 0, these are all hexadecimal representations, right? So when I say 0, it actually means 0 0 0 0 in a binary format. So all this is 4-bit values. So what this actually is, it will look like 0 0 0 0 0 0 0 1 0 0 0 0 0 0 0 0 in when representing it binaries, because everything will be represented in 4 bits. So we have our 1 here, and do you know the operation that we can actually take the 1 at the end and get 0 0, all zeros, and at the end 1?
Left shift.
Yeah. So we will left shift this value
8 times
with 4 into 2, because there are 2
Yep.
hexadecimal digits that we want to left shift by, and we will get 0 0 0 and 1. And similarly for getting the Y of F1 8A, we will AND it with 0 0 F0, and we will get 0 0 8 and 0, and then we will left shift by just by 4, because there is only one place we want to left shift by.
4 into 1, just to make it clear.
Yeah, good idea.
So just to give some clarity, left shift is just, as it sounds, shifting 1 bit to the left.
Right, so left
So we
shift
are
by
shifting
1.
8 times. So
Right.
it's like zeros. There are 8 zeros we want to shift out.
Correct.
So 1 will be shifted to the left 8 times.
And this is actually, though, don't think is like the C out, like the, in C in C out
Yeah.
use in C++, the pipe operators. These are not that. These are the these are the left shift operators that we have. So we'll take this information. If you didn't know about all these binary operations, it would have it's really important what we are about to do. So let's write our function called interpret instruction. Let's call instruction, and we will take in the instruction in here. Right. So first of all, Orko, tell me, you need to guess. Actually, I'm asking a question.
Yeah.
First of all, what should we do when we want to read an instruction?
You get the first bit and see what the instruction is, and then
Yeah, we
like
will do that. We'll obviously do that. But even before that, we need to do something.
even before that.
Yeah.
Okay. Like, what if when I get the instruction, what should I do with it
Right.
at the very first?
How we'll get the instruction?
I don't know, man.
We'll have to update our program counter.
Oh yeah, yeah.
So
Yeah,
we'll just use
obviously.
this.pc plus equals 2. Right? And why am I adding it with 2? Because each instruction is 2 byte long in the memory. So we'll add it with 2. And then like before anything, let's get the x and y values, because many instruction uses this x and y values, so it's just better to let's have it with us. So we will define x as instruction, and we will AND it with, as I showed you, 0x 0f 0, and then we will left shift it by 8. And similarly, I'll let me const y would be the instruction and 0x 00 f 0, and we will left shift it by 4. So we get x and y values. If it didn't make sense to you and you have skipped the binary part, so it is very advisable to watch that section and then come to this in case it doesn't make sense. Right. Now I'll put in a huge switch case here, which we will fill progressively for all the instructions that we might have. Okay, so let me copy paste it here. So what have I done here? Right. So you will see in the CHIP-8 instructions, all the CHIP-8 instructions that we have, some start with 0, some start with 1, some start with 3, some start with 4, and it goes all the way up to F. Right. So if we broadly classify all the instructions by starting with 1, starting with 2, starting with 3, starting with 4, we actually can have different cases for those, right? So first, if you see that we have taken a mask like 0x f000 to just get the first hexadecimal place and fill all the others with 0, so that we can have cases like 0x1000. So only the first digit exists, all others are gone, right? Now some digits, like if the instructions start with an 8, if the instructions start with an hexadecimal 8, then it might have 8xy0. As you can see, it may be 8xy1, it may be 8xy2. So for those, when I've got this, I actually I went ahead and I ANDed my instruction with 0xf, or which means just, I'm actually ANDing only the last part, right? Only the last digit. 0xf means 0x000f, right? So I'm ANDing only f to the last digit, and we are getting the last digit. And as we have already gotten x and y, we can actually use this value to execute the x and y values to execute these instructions. It might be a little overwhelming when you hear it for the first time. So I'll suggest that you maybe pause the video and take a look at the, all these instructions. So it will take a minute or two to settle down. That it might seem a lot, but it will be clear, because it's like following a manual. It is very simple. It's nothing very complicated actually.
This is what I was trying to say. So take the first one, then check.
Yeah.
Right. So these x and y, those are like the variables you want to perform something operation with them.
Yeah.
And the constants you want to have in different categories you want to put using the constants.
Right. So you see,
kind of like that you can.
Yeah, correct. Absolutely correct. And x and y, why have taken x and y out? Because see, there are many other instructions which don't have x and y, like a, n, and n, which actually has an address. So because x and y is so commonly occurring, it's better to just keep x and y out, right? In the first place. So now you see every instruction actually has this text format, which is kind of an assembly format, which tells us what to do, and this description will give you the detailed explanation of what it does. Now I won't actually go here and implement all of them, but let's implement let's import a few interesting ones to see how all this works, right? Make sense, Orko?
Yeah.
So sure. Let's go ahead with the first instruction, and this is like clr. What it does, it clears the monitor, right? This is what is in the description. So what I will do here in monitor, we define a function called clear. So this .monitor.clear will just clear out the monitor. Done. We have successfully implemented one instruction. Nothing complicated, right? So ret means return. This is again a very interesting, a bit of segue, but this is also a very interesting thing that happens in many systems, many architectures. And see, this is why we should do some projects like this, which is like implementing something fun, not something very practical, but implementing something fun to learn all these concepts. So what ret is when we are returning from a quote-unquote function. Now, when you're executing a function in a programming language, what happens? You go up till a point, right? You go up till a point, then you execute the function, then you come back again from the next point, right? So what is happening? We can imagine it like this. Like, let's say there is and as I talked about the program counter, which tracks the line of code that we're executing. Let's say there is a stack, that we have a stack, right? So we push the program counter that we are supposed to come back to from the, the other function on the stack. Then we go ahead and execute the other function. And after executing, where should we go? How do you know where is the place that we should go after executing the function? We will get that from the stack. So we will pop that value out from the function, from the stack, and we will keep executing. So we'll pop the PC out and we will keep executing. And this makes sense, keeping it in a stack, because there might be recursive function calls. There might be different one function inside another function. So those return points would be kept inside the stack and it will come back in. So this ret call actually returns from some function or something like that. So when returning, what we do, we pop from the stack and we put it in a program counter, right? So we will say this.pc is this.stack.pop. So right, we are done with another instruction. Nothing complicated.
So I can give a bit of analogy for this. So think about going to a friend's house, but you need to return back to your house. So you need to know your own address. The stack is like think it like a memory. You know your own address in your memory, obviously. You go to your friend's house, but when it's time to return, you know which address to go back to.
Right.
Kind of like that.
Also, like it might be like this. Like you go to your friend's house, you maybe keep your cap there, right? And you go to another friend's house, and while returning from that last friend's house, you cannot go directly to your house because you will leave your cap. You need to take your cap from the last friend's house, then come back to your house. So we are popping the last element of the stack, which is friend B's house, we take that, we go ahead and take the cap, execute that instruction of taking the cap, and then we see in the stack we have point A, which is our house, and we go back to our house.
You only return in the path you go in forward. That's
correct. And every part of the path, like breadcrumbs, we put in a stack. So let's get to another instruction, 0x1000. What does it do? So this instruction is jump to a particular address. So jump means this means to be 0 1, so 1 n n n. It means we have to extract this n n n value. We have to extract this 12-bit value to get the next address for our PC.
Store it in the PC. Yes.
Yeah, because then the counter will jump to it. So like something like go to, right? Now I talked about the ret call, right, where we are popping out the PC. Let's also implement this call ADDR. What does call ADDR do? Now we will be calling a function, right? So before calling, what should we do? Before calling, we should go ahead and push my current program counter onto the stack, because I need to know where should I return to, right?
Yeah.
Then set our PC to the address of the new function where the code should go next, right? So we'll say instruction 0x fff. What happened here? Yeah. So that means we are taking the last, so 0x fff, when we are just mentioning 3, it means 0 fff f, and what it does is actually gets the last 12 bits of the instruction, and we'll break out. Now let's talk about a branch instruction. Let's talk about a if condition. In C or Java, let's say we are executing a if condition. How does that go on internally? How is that happening with a very basic CHIP-8 kind of an architecture? So what we do here is we take a value and take a register's value, and we compare them, and we see that, well, if it's equal, then jump the next. So if it's equal, then don't execute the next instruction. If they are not equal, then execute the next instruction, right? Makes sense, Orko?
Okay. Yeah.
So what we do here is simply, if we check that v this dot v x, now you see that we are using this x variable that we extracted before, and as I told you that x and y comes up a lot, so let's keep using it.
What was this v, by the way?
Yeah. So v is the registers. We are represented by v.
Yeah.
So we have 16 registers, and the x here signifies which register I want to use. The 0th register, the first register, right? And we will be checking that if it's equal to the byte value that we have. So instruction and
I thought you were going to use double equals.
No. I don't want to be, it's like I have to use like in the original code there is a place where I've used single not equal to, because VS Code throws error when we're not using TypeScript and we are using single not equal to. Like VS Code just keeps that annoying red line. I don't like it, but what to do? So this is so we are checking that if the value of the register that is mentioned by X is same as the last 8 bits of the instruction. So KK represents the last 8 bits of the instruction, which is a byte. So and all our registers also have 1 byte values, if you remember. So we are comparing these 2 bytes and we are seeing are they same. And if they are same, what we plan to do, we will jump the next one. We will jump the next value. Simple enough. And see, the next instruction, that is SNE, means just the opposite. Means we are checking if it's not equal to, then we are jumping, right?
You can explain why +2.
Oh yeah, yeah. So +2 is, see, as we were doing before every call, right? We are increasing PC by 2 because we have got 2-byte instructions in the memory, and we are increasing the PC for to get the next instruction. Now, what will we do to jump an instruction? So next, let's say I'm on instruction number 5, right? On memory location 5, the next instruction is at 7, but I don't want to execute that. I want to execute instruction number 9. So whenever we see that, well, it's equal, I need to jump the next instruction. So I set my PC at 7, right? And then when the interpret instruction is, this will be called in a loop, by the way, when this is called again, then the PC would be increased again, and we will go to 7. Make sense? Sorry, we'll go to 9.
9,
yeah,
yes.
Correct. So we implemented up to S and E, right? Now the next instruction that we have is also kind of branching instruction, also kind of a conditional, which is comparing value of 2 registers, Vx and Vy. So X and Y are given to us, so we are comparing. If both are equal, then we are just adding 2 to it, right? Let's talk about one LD instruction, if I can find. Yeah, okay, the next instruction is only a LD instruction. So in LD instruction basically is for load, so it loads a value into your register. So I'll copy it to what it does. It takes the instruction, takes the last byte, FF, which is 4-bit, so last 8 bits of the instruction, takes the last 8 bit of the instruction and puts it in the VX. Make sense? Right. There is also this add, which essentially adds, takes a byte value, takes a register and adds it to the register. Let me just copy and paste code 2, right? Let's see some 800 instructions too. Now for till now, Orko, you tell me, till now does, when you
where is the adding one? Can you show me?
Yeah, this is just simple adding.
Okay.
We take a byte and we just add, mathematically add it. Now Orko, tell me, first it seemed that, well, how can I decipher all this? Now does all this instruction, when you see here the textual format of the instruction, does this make sense? Like tell me, when you see LD VX VY, what do you think it does?
Load Vy in Vx.
Correct.
Like register X, load the Y's value.
Correct. Great. Correct. What do you think OR VX VY does?
ORs the 2.
ORs the 2. And what does it put it?
In Vx.
Correct. So you can interpret the instructions like this. And Orko I actually hadn't told Orko the answers to all this. I mean, I actually hadn't talked to Orko about this, what we're going to do. So yeah, he's actually learning it now. So we will actually not sit out and implement all these 8 instructions. Yeah.
Which one?
Maybe actually we can talk about the add VXVO instruction. Why is this interesting? Let's understand. So in the registers that we have, the last register, the V15 or the 16th register is a very interesting register because it is used to store carry forwarded values. Right? So when we add 2 values of registers, right? When we add values of 2 registers, if there is a carry forward value, and what we mean by carry forward value here is if it's greater than sum of both of them, it's greater than 0xFF, right? Or it takes why it's more than 0xFF, because that's the maximum 1 byte can hold, right? And all the registers are 1 byte long. So if the value overflows, then we set the VX, the V15
to 1. To carry forward. Yeah, just to say that it has actually overflown. And we do this the same with with the sub instruction, which means it's with sub and both sub n instruction, which means subtracting. And if it goes below 0, let me just show the code here.
So if it goes below 0, then we take that 15th register and store 1 in there, the carry forward value. Now let's see this 06. Do you understand what this does from the text?
R&D. I don't understand what is R&D.
Okay, it means random. So I've copy pasted the random R&D instruction here. So what we do here is that first we have vx comma byte. So we have a reference to a register, and then we have reference to a byte. So what we do here is we generate a random number, then we take the random number and perform an AND operation with the byte value that we have been given, right? So instruction and 0xff, it gets the last byte value. ff again extract the last byte, because f and f means f and f means 4-bit plus 4-bit, which means 8 bits, which means 1 byte of data, right?
Why do we AND it though?
Just this is the, I don't know exactly the exact reason, but this is the specification. Maybe their way of generating random numbers the way they want.
Never doubt the specification.
Never doubt the specification. The specification is now the Bible for you guys.
Yes.
So
too holy. Oh, why the let though? Can't you use const rand?
I can use constant. Thank you for pointing that out. I can use constant. You know, these are the reasons why I have demoted you down from Minecraft to Space Invaders.
Okay.
Okay. Now I'll copy paste a big portion of code in the drw. Okay. Before you tell, let me change this to const. Right. So drw, what does that do is it takes the x and y values. It takes the x and y values. It treats those x and y values as register references, and in those registers we have stored coordinates to load a sprite, right?
Okay, yeah,
right. And
so the xy coordinate to display the sprite.
Correct.
Makes sense.
And how we are getting that? Let's say we have defined the width to be 8, and what we do here, we iterate through row goes to row of height, row less than height. Now what is this height? Height is the last 4-bit. Now nibble, if you don't know, nibble means a 4-bit value, byte means a 8-bit value, and nibble means a 4-bit value. So we go ahead and take 0xf. So we take the last nibble. So what we do here in the for loop is we iterate number of times as we have got the nibble value, and we have put it in height. So what we do is we iterate from 0 to the value that has been given to us from the instruction, and we load that memory. And on what basis we load that memory? We takes the index pointer, and that index pointer can be set by an instruction. We take the index pointer and add it to the value that we have. So you set the index pointer, you tell them what row that how many rows or how many places that this needs to go, or how many rows your sprite is long. So your sprite starts at this dot index and it goes up to this dot index plus the nibble value that you have given. In our case, this dot index plus row, right? So this enter value, so you set the index value to your start of the sprite, and then you will give the length of your sprite with the nibble. And then we go to call width. Now we have given a fixed width of each sprite, which is 8, and we draw it on the screen. Now why we are drawing it. While we are drawing it, we are also getting back a value that if the pixel has been cleared or not. And if it has been cleared, we are setting our special index, the special register that we talked about, the last register, the 16th register, we're setting that to 1, so they can detect collisions. So if the bullet hits the monster, they get to know. If the enemy hits you, they get to know. So let's say our sprite, let's go to some default sprites. So let's say how we represent 2 here. Each row here is a byte. So how are we representing 2? 1, 1, 1, 1, and then 0, 0, 0, 0. And we are putting one value here, and we are actually making this 2 shape. So first we are checking that if this bit is 0. Now why I have set my width to 8 now makes sense, because we are talking about 8 bits here, because each it is 8-bit value, and each bit tells us should I turn that pixel on, or should I turn that pixel on, or should I not set that pixel, right?
Yep.
So we are taking this value, then we are checking this value, then we are moving the sprite by 1, so this gets right shifted. Then we are again checking the first value, because it is 0x800, the first value is 1000, and then again followed by zeros. So then we're checking this value, then we're checking this value. So like that we can see if there is like what shape that sprite is giving us. Does that make sense? Or it's a bit complicated, but does it make sense?
Explain me 2 things. What is this dis.index? What was the value of that?
So dis.index is where your sprite starts in the memory.
Yes, 0x200.
No, 0x200 is where the PC starts.
Oh, the PC starts. What was the value for the sprite?
So this.index, you will mention it by your own. So the programmer actually creates this sprite. So these are some default sprites for 0, 1, 2, 3, 4, 5, 6. Okay. So these are the some that it's stored in default, and I'll show where these are stored in the memory. They have some default values to be stored. But
this.v0xf equal to 1 in the if condition.
Yeah.
What is that for?
Yeah.
Collisions, right?
Collisions. Yeah. So if we are checking that if that current, like we remember we returned true and false from that set pixel function, and if we have cleared out a pixel, that means if 1 and 1 is there, or maybe there is a collision or something like that, then we are returning 1, or that pixel has been cleared.
We did a XOR, right? Can you open the function? I forgot.
Sure. We did a XOR. It cannot be opened from here. Yeah, we did a XOR. In CHIP-8, whenever you set a pixel, it means you are XORing it by 1. Understand?
Okay.
So we are setting that instruction, and yeah. So index pointer would be set by the programmer wherever the sprite is. So let's say, they want to draw out a triangle, so they will probably set this one, and this one. And then I'll again set this row 1. Then it will actually form a triangle, and they can put this on the screen.
Yeah, and what about the sprite right shifting to by 1? Why is that?
So tell me one thing. How will we understand that a bit of one row, like you see one row of the sprite, this row,
okay.
How will we understand if a particular bit is 1 or not? We are ending with so we are ending it with 1 and followed by all zeros, right? So so we can only check the first bit. So another way we could have done is first end it with 1 and all followed zeros, then end it with 0, 1, and then all zeros. We are not doing that. It might be a bit complicated. So what we are doing is we are right shifting the sprite itself, the byte value by 1, which is single row of the sprite, and we are shifting it.
Yep, makes sense.
Makes sense? So let's see what all we can do. So this E values, these ones, these are actually will be able to implement when we have implemented our keyboard. So let's skip it for now. Okay, let's do this one. 1x1 E, I guess it actually increments the index pointer. So let's say I have got a sprite somewhere, and then I want to increment it by some value to get our next sprite. So we can do that. So we can add it this dot vx, sorry. So it adds to the index pointer. Whenever you see I in the instruction, that means index pointer.
Okay.
So can you tell me, Orko, what does this I in third brackets mean?
Array of I?
No, it means the location of the index pointer.
Okay, the address of I.
Yeah, the address of I. Sorry, the address of I. So it means the address that is represented by in the index pointer, right? So like let's say this LD in the location of I vx value is taking all the register value up to x or up to vx. Let's say I say 4, so 0 1 2 3 4. It's taking all the values and putting it in memory, in the RAM. Maybe we will use it for some sprite, or we will use it for some other cases, right?
Okay.
This makes sense.
Taking all the values of the register.
Right,
Passing,
yeah.
right?
So we are taking the registers value and loading it into the memory. And there is another instruction, the next instruction, which which takes the values from the memory and puts it in the registers. So we will cut from here, and I will actually copy paste all the instructions here, because going through all these instructions does not make sense. I think we have discussed a fair bit. What do you say, Orko?
Yeah, sure.
So what we have done is I have copy pasted all the interpret index instruction code, and we will be referring to this part more than once to see what all instructions are there. So if you don't understand some code, if you don't understand the explanation, and if you go ahead and see the code and still don't understand it, let's leave a comment and we will obviously address it if we have the answer, or we will direct you to somewhere that you can find the answer. And also it will give us YouTube engagement, guys. Yeah. And on this point, leave a like. Like if you have made this far, then do like the video and do subscribe to the channel. So if I made it this far. So
at this point, we might be just talking to our own selves, nothing else. But
we can actually.
Even if we sing a song, nobody will hear us.
Yeah. So okay. Now I was talking to you about some default sprites, right?
Yeah.
So what we can do is actually we can copy some of the default sprites here. Now, according to the specification, there are 0 to 9 and ABCDF, all the hexadecimal digits. All this sprite should be kept at 0000 location. So they say that in the memory map, if you come, they say that 202 FFF is the program space, and they haven't mentioned it here. But before that, from the 0th location, they expect all the hexadecimal digits, all the default hexadecimal sprites to be stored. Yeah, they have said the data should be stored in the interpreter area of the CHIP-8 memory 0x000 to 1FF. So we will store all the default sprites that we have. Now what this hexadecimal numbers mean, if you see here, it actually represent each row of the sprite. So this means 0xf0, this is 2, right? So if you can see, right, it's pretty simple, and we just store it in the memory. Now we have to also write a function to load the program in memory, right? So let's load the program. So what we are doing here is we have taken a program which is, we expect that to be a uint8 array. For now, we expect that program to be an uint8 array, and we have started from the location 0x200, because again, that's where the program should be stored in the memory, starting from 0x200, and we have copied whole program in memory. Let's talk about another function called update time. So after each cycle, the timers that we set would be decremented by 1. So if it's greater than 0, the delay timer is greater than 0, we will negate it by 1. If the sound timer is greater than 0, we will negate it by 1, and we will see when we are calling the update timers next. So Marco, how can we talk about, how can we tell about the CPU cycle? What is a CPU cycle? So let me copy the cycle code. Right, let's talk about this. So it will, we have taken a constant called speed, and what it does, it for one cycle it will interpret, the CPU would interpret one batch of instructions. So let's say speed is 10, so it will interpret 10 instructions, right? So, and there is, and the VM might also be in pause state. So if we are checking, if it's not paused, then we are doing this. Olga, can you tell me why are we doing this?
I don't know.
So tell me how many bytes our instruction is.
2 bytes, right?
So it's a 2 byte or a 16-bit value, right? So we are representing it by 4 hexadecimal digits, that, and each is 4 bits. So it's 2 byte value, right? So when we are talking about this, so what we are doing is we're taking the current memory location, and each memory location is 1 byte long because we are representing it by one uint8 array, right?
Yeah.
We're taking that value. So let's say it says, let me put a comment.
Okay,
here.
makes sense. Yes.
So let's say that says FF. It's a 1 byte value, right? FF. The next pointer says 44. So what we are doing here, we are first taking this value and shifting it by 8 bits. So let
FF00. Yeah.
FF0. Then we are adding it by 0044, right?
Now it's FF44.
Now it's FF44. So we are appending 2 digits, appending 2 values, and we are getting one instruction, and we are passing it to our interpret instruction code. After, every cycle, we will update our timers. Now we haven't implemented the speaker yet, so let's comment this out for now. This is we will make some after every instruction we will see after every cycle we will see that if we need to make some sound or not, and then we are using this .monitor.paint to check that if to paint whatever to because the instructions are making some changes in the display, so we will now go ahead and put it on our screen. We'll go ahead and put it on our canvas. Yeah. So are we done with all the functions here? Yeah, we are actually done with all the functions here except sound, which we will implement after we are done implementing our our speaker. So let's go ahead and talk a bit about our index.js. Let's glue up some of the code and see that if are we able to run any ROM. Now let me confess, guys, I haven't tested with just the monitor and the CPU to run any. I at least implemented the keyboard. Now there are many instructions which are using the keyboard. So if we go to our CHIP-8 class and see, there are instructions which are using this .keyboard, and we haven't defined this .keyboard yet, so there might be that this .keyboard is undefined. There might be those errors, but I think there is one ROM which has no keyboard or sound instructions, and we can use that. So we will try, and this is the first time I'm trying it, so yeah, no worries.
I thought I will never leave that CHIP-8JS file.
No, we are done with that. Actually, we are done with that. So let's now do something. Let's now load our ROM from the internet.
CHIP-8.
No, let's now load the ROM from a server. Like our ROMs would be kept on a server. Let's just download the ROMs and we use it. So let me declare this. It's the URL, and we have some name called ROM name. So let's some variable called name. Let's actually declare a function called load ROM, right? And let's accept ROM name in here. Cool. Does that make sense? Yeah. Let's put it here. And now we will actually fetch our call. So let's use fetch the URL. And if you don't know about fetch calls, I have a video on about that. It was actually my first video on this channel, so you can take a look at that, or you can, you know, just Google it and take a look at MDN or something like that. It's nothing much. So we on fetch will handle the then call with the rest. And Orko, what do you think we should return from this function?
I don't know.
Like
The binary.
Yeah. How do you know how to what call gets binary values from a response? What function name?
Never had to use it.
So it's called array buffer.
Okay.
I also never had to use it. I learned it just now. And we can
Interesting.
then that will also return a promise, so that will also give us a buffer. Now what will we do with that buffer is we will convert that buffer into a uint8 array, because as I told you, our CHIP-8 class expects the programs to be uint8 arrays of right. So now is a bit of code that I'll copy. So 1 minute, right? So there is some division magic that we're doing. Is we are what we are doing is we are actually taking a FPS value and we are sticking to that. Now, so first we will call the load. I actually have made a typo there. Load sprites into memory. We'll call this function now. Then we will load the program into the memory. Does that make sense, Orko? And then we will call request animation frame of some function called step, and now we will define the step function. So let's define step.
So you keep giving third brackets.
Yeah, I don't know why. I don't know. I don't know. I my shift is not probably that sensitive. So the step function is actually seeing that actually taking care that we are sticking to the FPS, and for each 60 frames a second we are calling CHIP-8.cycle. So we are calling one CPU cycle. Does it make sense? And then we are again calling request animation frame with step. Now when we you see that we have a variable called loop. Let me actually copy.
Where is the then? Where is the then?
For what?
No, minus then. Where is the then? Okay, you have declared it at the top. Okay, yeah. Okay.
Right. And then we are cycling the CPU. So let's try to test this. I am nervous, but let's do it. Let me remove this pointer test render and let me call load ROM. And I think the picture ROM would suffice if I'm using. Now we can't actually anymore use the parcel dev server, and we have to actually run a actual server after building the whole project. And do you know, Orko, why we can't use it? Can you guess?
Nope, I don't see why.
So what it does is that parcel dev server returns that binary file as text format.
Why?
Yeah, I know it's a dev server. It's probably not that. Yeah. Okay, so we haven't actually installed Express yet. Why is that? So let me install Express. It will take a bit. I don't have very fast gigabit internet.
We'll cut to it.
So we are again back at our browser to see why stuff does not work. And it says that CHIP-8 is not defined. Orko, why didn't you tell me?
Line number 27. It's not my fault.
It is your fault. Because we haven't imported CHIP-8. and we haven't even.
Oh my god.
So let's import CHIP-8 and make an object out of it. Con CHIP-8 equals new monitor. Sorry, no, CHIP-8, and we will pass in the monitor. Now the problem of having a server like this is after every change we'll have to build it again and serve it. So let's now, is this working? The weird browser that we have here, which is completely useless. Yeah, it is completely useless, or maybe our code is still not working. So let's go ahead and see why it's still not working. uint array is not defined. Okay, so we are back at our VS Code, and we will now put our, and we'll see that why our code is not working. As it was saying that it cannot find uint8 array. Now I think I have probably made.
Still in index.
Okay,
Is open
no,
on the side.
yeah, probably made. I wrote uint8 array as unit8 array. Live, like I like to make this live coding format videos, which is nearly live videos, even though we are not streaming it live, but it has its problems. So let's again. Okay, so I think we have got something in our hands. I think our monitor is working.
Yes, CHIP-8.
Yeah, I think that there is a white boundary here, but you cannot see it because all the background is also white, but there is also white boundary here.
Okay.
Yeah, so yeah,
I believe you.
You should believe me. I mean, what else have you got? What other options have you got other than believing
Nothing. I'm on a screen share. I can't do anything.
me? Yeah, you cannot actually. So now we are remain with our keyboard and speaker code. It won't be much difficult to implement our keyboard. Actually, it won't be much difficult to implement our keyboard. So let's implement the keyboard.
Zoom in.
Oh, I haven't zoomed in, right? Yeah. This live coding format is interesting to make. It's easier to deliver. I mean, it's not. It's more genuine. It's a more genuine format, so the students can actually understand better. Like I understand better from these kinds of videos because I can see the bugs that are being made, so I can stay cautious of those. But yeah, it's a pain to make these videos and it's a pain to edit these videos, and I will waste my Sunday on editing this 2-hour-long video. I hate my life. So the CHIP-8 keyboard has all this keys 1 to 9 and A to F. So these are all the keys that they have. Now we will map this keyboard to our own keys, right? So to do that, in our constructor, let's have this key map. Right, now this key map actually doesn't map 1 to 1 key 1, like it maps 1 to 1, it maps 2 to 2, maps 3 to 3, but it maps C to 4, and then it maps 4 to Q. And why is that? Because see, the format that they have here on a QWERTY keyboard would be like the 1-to-1 mapping would be, if we map exactly as the numbers and the letters here, it would be impossible to play the games. So in the article 2, I've seen that they have mapped the first 4 keys of each row to these rows so that the games are actually playable. And we'll have some variables. Let me just copy paste them. Okay, let me close it and collapse this. So we have got keys pressed, so where we will keep track if the keys are pressed or not. And this is actually a function on next key press that we will be sending from a CHIP-8 JS class. I will see how that's done, because in one instruction we will need to have a callback to manipulate some register values, if I remember it correctly. So let's define a function if the key is pressed. So we will just return if this dot key is pressed is key code. Then we will we will define on key down function. Now what is it doing? It is saying that that key is pressed, it's turning it to true, and it's calling this on next key press value. Now the on next key press would be this function would be actually passed by chip8.js, and I'll show you how it's done and why it's done. And we'll go ahead and say on next key press is equal to null. So after every run we will remove remove the function from existence. And we'll also define our on key up function, and we'll export default the class keyboard. Cool. Now let's go to our CHIP-8 class, right? And accept a keyboard, and let's say this dot keyboard equals keyboard. So we have set our keyboard value, and now we will check out some keyboard instructions that we have. So we are again back to this huge switch case of instruction. Let's try to find a keyboard instruction. Okay, see, now we have a instruction like this, like skip vx. So what does this do is it if the key which is represented by whatever value is in the register x, if that key is pressed, then it will skip the next instruction. And as I told you, why we are incrementing PC by 2. And there's the skip sknp, which is actually if the key is not pressed, then it's going ahead with the next one. So this one is the instruction where we need the key input, where we need that weird function. So first of all, this pauses the machine and does not unpause it until we actually press a key, right? Okay. So that's why we have defined this callback, which sets this dot vx equals to key and this dot paused equals to fall. Now this value is a part of the CHIP-8 class, right? That's why we have to define it as CHIP-8, and when setting the value, we have to take that function name and we have to bind it with this. Now bind, when you call a bind on a function, what it does is it provides this value for that function. So in that function, whenever we use this, it would mean the value of this that we have passed from the bind. I have a dedicated video on bind, so you go ahead and check it out. Self-promotion. Arko, you want to say anything about this?
At this point, nobody's watching.
Right. So we haven't declared our sound yet. So let's do one more test. With only our keyboard and our monitor, no sound. Let's see if it works or not. Okay, let's not forget it this time to import the keyboard.
Yes, you have to import the keyboard.
Like, why didn't you tell me last time? It's your duty, right?
I was not hired for this.
You are not hired for anything. I'm not paying you, know that, right?
Then why should I do anything?
As a friend? Okay. So we have got our, let me declare new keyboard. Why are we passing anything here? Let me put it above the CHIP-8. and let's pass keyboard here. I'm really skeptical if it would work. Let's go ahead and try. There is nothing more important in this world than trying. There's some
words of advice.
Yeah, there's some life lessons thrown at you right now.
Yes.
Let's go to localhost 3001. Okay, it still is loading the CHIP-8 CHIP-8 ROM, which is useless for keyboard. Let's use Blitz. You know why I am keeping the speaker for last? Or any clue?
Is that? It is horrible.
The sound it makes is horrible. That's why.
It's horrible.
Okay, so we can see, let me unzoom it a bit. We can see Blitz here. Okay, now see the keyboard is working.
Dropping bombs left and right.
These are not bombs, actually. These are food packages, and we are throwing them on.
Yes, we are.
What throwing them on? Come on, man. Think of something. Think of some.
This is a rescue mission.
Yeah, and we are throwing it on. What are these things? What are these stuffs can be called? These are the hunger levels of people. No, so they're taking it and they're
buildings. Like there's a flood and the people are stuck on top of buildings.
Yeah. So there's no.
You go biryani.
So no war involved here, guys. No wars involved.
Just dropping some friendly biryanis.
Yeah. Yeah. Let me again zoom in, and we have successfully implemented our CPU. We have successfully implemented our keyboard, and we have successfully implemented our monitor. I cannot believe we have come this far into recording this video. I still don't know why we are making such a big video for this. CHIP-8 in one video. I just got the title. CHIP-8 in one video. Right. Now let's go to the last phase. Let's implement our speaker. Where is the speaker? Okay, it's opening there. Let's come here. Okay. Let me collapse this, and we are now going to implement our speaker. So in the speaker, we'll actually use a bit of what do they call it? Web audio API. So let me just declare this class speaker, export default speaker, and go ahead and declare the constructor. Okay, so let me copy paste the code in the constructor. So I really don't want to go into depth of web audio API, but we can. So web audio API is for managing and analyzing audio on the web, on front end through the browser. It's a browser native API. So we have used window.audio context. Now I think it might not work in Safari because we have to probably initialize there with WebKit audio context. I don't know. I don't remember.
So we don't care because we don't have a MacBook.
We don't care because we don't have a MacBook. Correct. We don't even have an iPhone.
Yes.
And this resume calls are there just to make just because there are some weird errors that sometimes come in web audio API if you don't call resume with gestures, and I just want to get rid of those, and sometimes the audio does not start. Now let me copy the play function. So what does this do? Now a thing about web audio API is it's like a graph. So in web audio API, what we do is we declare a graph of audio nodes. So we might have a source, then we have some nodes in between them, and then there is the destination, which is our speakers, right? So what we create here is we create an oscillator node. So oscillator node will have a kind of a sine wave. So like here we are using a square wave. It might have a square wave. It might have a triangular wave. It might have a sine wave. So it creates a wave, and it just keeps on outputting that sound, right? And we are setting the frequency to be 440, which is a constant. And we are starting the oscillator, right? And also look at this method called connect. As I told you, it's a graph. So we are taking the source, which is the oscillator. We're connecting it to the destination, which is the speaker, right? In stop, we are actually removing the oscillator completely, because we cannot call start on one oscillator more than once. It's weird. So let's go to the CHIP-8 class and see how we are using our sound. Right. So let me unzoom it for a bit. Yeah. So as I talked about was the sound timer, right? Yeah, the sound timer. So what the programmer does is they keep the sound timer to be, let's say, 10. So the sound would play for 10 cycles. Let's say they keep it for 5, then the sound would play for 5 cycles, right? So we will actually make a function here called sound, right? So the sound function would be nothing. It would be very simple. If the sound timer is greater than 0, it will play. The sound timer is,
I will stop.
It will just stop, and it stop if it's already stopped, then in the function we have checked that if the oscillator does not exit, then nothing will happen, right? So, and after every cycle, where is my cycle code, we will have to call the sound. So to check if any sound should be playing, should we make that sound? Let's also accept a speaker here. Let's
At the timer, it's still 0.
Yeah, the sound timer would be 0, right? The sound timer would be set in some instructions by the user.
Okay.
So there is this instruction LDSTVX, so it will load the VX value into the sound timer.
Okay.
You understand, right? Simple. So if you want any detail about any more instruction, if you want to understand deeply, just write down the instruction in the comments and we will try to help you. So let's go to the index.js file and pass in our speaker. So import speaker from speaker, and we will make a object of that. Now also one thing I need to do,
pass in the object.
Yeah, we will pass in that object. We will pass in the object.
Okay.
No worries, man. I have forgot to link the style sheet. So link CSS, right? And yeah, I forgot to pass that, right? So let's go to index.js and pass the speaker 2. Which ROM should we use now? Do we want Space Invader? Let's go ahead with Space.
I have been waiting for this.
Let's go ahead with Space Invader. Probably not
work. This is my moment of truth.
Probably not work. Probably not work.
Probably not work.
But let's see. If it works in the first time, there's something wrong with it.
Yes.
You see, there is something wrong with it.
It's always something wrong.
It says it cannot find style.css. Okay. So for parcel, we cannot actually pass it like this. We have to mention. Okay, so it's not actually there, right? It's in src. You have to mention it, the proper path. So it will package it will copy the CSS, minify it, and do all the fancy stuff. Parcel is great for small project with so less configuration. Parcel gives everything out of the box. It's great if you want to use. So we are here at the browser to check that if the audio is actually working. So in Space Invaders, I think you have to actually hit one of these guys to get the audio. So let me try to hit them. I have hit it one. Okay, why can't I hit another? Okay,
pathetic. This is what I have trained you for.
Okay. See, it's working. We have actually made a VM. We have actually made a working CHIP-8 VM, and we are now playing games on it. Now, if you want more detail, you can actually see the code in the description. All the CSS and all the fancy stuff is here. Why are we hitting little androids? Android heads. So all the code is actually there, and you can see it, and we have the ROMs are also there, and The demo link will also be there. It's chip8.imankush.me, where you can actually select the different ROMs and try them out. You can't see the, what to say, the drop down in the OBS. So this is the sound why I was not implementing speaker. So that's it for this video, guys. We have implemented a complete CHIP-8 VM from scratch. We try to understand concepts of how architectures in general work, and this is our first time making a video like this, such a long video, such a long tutorial. So if there are any mistakes, please forgive me, but I think you might have, if you have followed the whole video, if you have learned a lot. So leave a like for this video, subscribe to the channel if you want more content like this, where we really go into the depths of discussing something and trying it out in practicality. And if you think your friend or anyone would be be benefited from this video, do share. I mean, that is our dream. If you share, that will help the channel a lot if you share. So thank you for, if you've stuck till the end, thank you for sticking till the end, and see you in the next one.